The next thing we'll talk about is this theorem, which says that continuous branches of log are analytic, which also means that they're holomorphic. So how does this come about, or how do we find analytic or continuous branches of log? Well, here's sort of scratch work. If we had an analytic branch of log, then I claim that its derivative has to be 1 over z. That's just because if I have f holomorphic satisfying this equation, then you can just solve that. If you take the derivative of both sides, we'll get x of f, which is z, times f prime equals 1. So you get that the derivative is 1 over z. So you can construct analytic branches of the log by just finding antiderivatives of 1 over z, and we can do that because we know that 1 over z is analytic, and we can find antiderivatives through power series. So that's how we're going to do it. So suppose that we have just one inverse image under the exponential map of z naught. So x of w naught maps to z naught. And we already know that we can construct antiderivatives of 1 over z as power series. We did that in the section on power series and analytic functions. So let f of z be an antiderivative of 1 over z given by a power series centered at z naught. And we have a choice with an antiderivative of its value at any specific point. So we're going to make it be the right preimage. So we're going to have f of z naught equals w naught. Then f will be a branch of log, which exactly means exponential of f equals z. And we basically just have to undo what we did in the scratch work. We can build this f to be an antiderivative of 1 over z, and so if we take this derivative, z e to the minus f, well, you can guess what will happen. I wrote it here. We're going to get 0. So here are some of the details. If we take this derivative, we'll get 1 times e to the minus f minus z e to the minus f prime. So we'll get that f prime times z is 1. So we get e to the minus f minus e to the minus f. So we get this is identically 0, which means this function is constant. So we can plug in a specific value to see which constant it is. So if I put in z naught, I get z naught e to the minus w naught, and we have e to the w naught is z naught, so this is indeed 1. So you get that e to the f of z is identically z, so it's a branch of log and it's analytic by construction. Earlier we mentioned that we can get branches of the logarithm by just restricting the exponential map to strips, I guess horizontal strips of width 2 pi. So suppose we have one of these. So suppose L is a branch of log, and the imaginary part of L is between a and 2 pi plus a. Then this function will be analytic. So this includes the principal log and the log tilde that we defined before. And basically we just have to show that this function is going to agree with the analytic branch of log that we already built. So how does this go? Well, we fix a point in the open set that it's defined on, and we can build a power series, as in the previous lemma, on a small disk around z naught that matches the value of L at z0. And then since f will be analytic, well, it'll be a power series, so it'll be continuous. So we can shrink r if necessary so that the imaginary part of f of z is trapped between these same two values that the imaginary part of L is trapped in. And then what do we get from that? That, well, the real part of f and the real part of L have to agree because they're both branches of the log, so it's just natural log of modulus of z. But then since they're both trapped in these same intervals, their difference has to be less than 2 pi, and two values of log that are less than 2 pi in distance, well, they just have to be the same because two different values of log have to differ by a multiple of 2 pi I. So we get from this that f has to agree with L of z, at least on this small disk that we were describing. But then this just tells us that L agrees with a power series on a disk centered at z0, and that exactly means that L is analytic. So now let's prove the theorem that was mentioned, that continuous branches of log are analytic. Well, if I have a continuous branch of the logarithm, then locally we'll have the property of the previous lemma. So at any point I can look at a small enough disk where the values of the imaginary part are trapped in an interval of length less than 2 pi, and that restricted function will be analytic, but being analytic is a local property, so you automatically get the proof of the theorem. So continuous branches of the log will be analytic. So now that we know that these different logarithms are analytic, we can define power functions, and we will know that power functions are automatically analytic.